Picking up where we left off last time, this is an image taken from near Jasper in Jasper National Park in Canada. And what we can see here is a freshwater lake in the foreground and the recharge zone here, which is going to be snow covered about half of the year and mostly dry the other half of the year. And here we see evidence of forest fire. So this implies a change in hydrology over the lifetime of this forest, in fact, fairly recently. And if you've been in Canada over the last 5 years or so, you know that there's been a significant increase in forest fire coverage and damage because of the ongoing series of droughts. Flipping over to Ireland briefly, we're going to start talking now about surface storage of water runoff, where the water goes once it falls from the sky, and where it stays once it falls from the sky, at least temporarily. So these include lakes and reservoirs, like the reservoir we saw, the most artificial of reservoirs, Tom Sauk Reservoir of Missouri, an artificial reservoir on the top of the highest mountain in the state that was filled nightly and drained during the day, and it collapsed catastrophically, ultimately. In natural lakes, something similar yet opposite happens, as we'll see. So this is an image of myself and some students from a coring operation in Ireland, a place called Annock in County Mayo, which is in the west of Ireland. And what we're doing is taking a lake sediment core to evaluate how hydrology of this part of Ireland has changed over the last 16,000 years. This student of mine, Scott, suggested, why don't we just core right now? I don't think it's going to rain. And I said, I think it's going to rain, but okay, let's get it over with. It rained. Yeah. Here we have a series of diagrams illustrating the similarities and differences between artificial reservoirs and natural reservoirs. So starting with the artificial reservoir, during a dry period, we're going to have a limited input of stream water to the reservoir, and it may or may not increase the volume of the reservoir, depending on the outlet. If we turn off the gate here, we can retain all of the water and fill the reservoir, but that's going to affect the riparian environments downstream that are dependent on this stream water. In the case of wet periods where we have high runoff, we have the opposite problem. Now our gates are open all the way, and it's still not sufficient to drain the lake. So in the case of Tom Sauk, what they did was pumped too much water up into the lake and they overflowed it and destroyed it. In the natural world, it's a matter of not being able to release water quickly enough, and ultimately the dam can be overtopped, which can lead to its destruction and flooding downstream. In a natural lake, during dry periods, the smallest superficial expression of the lake is going to be exhibited. So as long as water is flowing out, the lake is going to reach some minimum size and stay at that minimum size. If that water stops flowing out, the lake can continue to get smaller and actually dry up completely. Now the value of the wetlands comes in here, and the wetlands are large sponges essentially, and wetlands can serve to absorb enormous amounts of water during wet periods and then release that water relatively slowly during drier periods. So that's one reason that we value wetlands. We don't tend to like them because they're swampy, they're wet, and that's not our kind of gig. Of course, there are a lot of animals that love that kind of environment, but we don't see them as cute and cuddly, so we tend to discount the significance of wetlands. When water enters the ground, it becomes groundwater, and it's now constrained not by the surface area, the volume of that groundwater at the surface, but by the volume within grains, within rocks below the surface. And this is going to be described as porosity and permeability. More porosity means more space, more pore space. These are pores between the grains. More porous is generally the case when grains are uncemented. Once we start cementing these grains together, we're fusing them by growing calcite grains between them, and that takes up space. Because the calcite grains, the cement, is taking up space, there's less porosity for filling with water. In the case of sorting, well-sorted sandstones tend to display more porosity than poorly sorted sandstones. And this is essentially the way concrete is made. We have big chunks in the concrete and we have progressively smaller chunks in the concrete. And the reason we have this variety of sizes is this. We take up space with cheap grains of sand and gravel as opposed to expensive cement. So poorly sorted sandstone has a much lower porosity than well-sorted sandstone. Poorly sorted cement is cheaper than well-sorted cement. When it comes to fractures within a generally impermeable rock like shale, that opens up conduits for water to flow. It opens up space for water to fill, therefore. So this impermeable rock, by fracturing it, will open up pore space and open up flow patterns. This is why fracking has become so important. It's a cheap way to get at natural gas and oil. It's fairly destructive, which is the downside, in that it destroys aquifers. It doesn't last very long. Permanent contamination, if that's your scene, fracking is the way to go. An issue we may have here, is that very fine-grained material like silt and clay can eventually fill in some of these conduits. Some of these tiny little pathways can get plugged up. So again, that's where fracturing would come in. It would disrupt these plugs. It would open them up and allow gas, oil, and whatever else is in the rock to flow out, as well as contamination to flow in. To categorize these here as rock or sediment type, which is not one word, versus porosity and permeability. Gravel, large blocky angular chunks, very high porosity, very high permeability. Coarse to medium grain sand, high porosity, high permeability again. Now as we're getting into finer and finer grain material, those grains start to block the passageways. They block the pore space. Porosity goes to moderate and permeability goes to moderate to low. Moderately well cemented sandstone has moderate to low porosity, low permeability. Fractured shale or metamorphic rock, low porosity, very low permeability. Unfractured shale, very low porosity, very low permeability. This rock is very good at blocking water flow. And we can see a bit of that here. We're going to take a look at a cross-section of soil and bedrock. And we have a couple different zones here. The unsaturated zone is known as the Vadose Zone. This Vadose Zone is important for plant growth. Plants generally require some kind of gases in the soil. And if they don't get those gases in the soil, it will kill the plant. Now, some have adapted ways to aerate their roots by producing little structures called knees that stick up. They look like pencils or spikes, death spikes coming out of the sediment, particularly mangrove environments where you see these things. And it makes walking uncomfortable, and you throw in a few alligators, and that puts the excitement back in. So these zones, again, are important. If the Vadose zone gets flooded, that can be very, very bad for plants that live above. Of course, any animals that live in the sediment pile that's flooded have to get out. Okay, so we have water and air occupying pore space up here in the unsaturated zone. Below, we have partially weathered to unweathered bedrock. This is going to be porous to some degree as well. It's going to tend to fill with water and be completely saturated and stay saturated. Eventually, if we wick enough water away through the Vadose zone, we can dry this out. That usually takes a fairly considerable drought, and people generally abandon the farmland. When discussing flow, we have inflow and outflow of groundwater. The recharge is going to be carried out by influent streams. This is a 360-degree image of Indiana, a place called Lost River. And this Lost River is almost 90 miles long, 140 kilometers or so. Of that, 23 miles, or nearly 40 kilometers, is underground. You don't see it. So here we see the river briefly, and then it's gone. And where it goes is down a sinkhole. These sinkholes are all connected together. This is all limestone underneath here. And this limestone underneath here is like a big sponge. It's got lots of holes, nooks, crannies, known as caves. And these caves are perfect channels for water. So the river disappears underground. It reappears as an effluent stream, and then it re-enters the ground as an influent stream, exits as an effluent stream, enters back and forth, over and over again. This also happens in volcanic regions where lava tubes substitute for these carbonate rock caves of Indiana. Now here's an example of water pouring out of an aquifer. In this case, the aquifer is known as a perched water table or perched aquifer, and therefore it's been recharged from above. That water that's recharged from above reaches an aquitard, something that's impermeable to water flow, somewhere in this rock pile. And the result is water flows along that impermeable surface till it reaches an exit, which is this spectacular waterfall out of the side of a very dry desert canyon wall. And this brings us to us. And if you're living in Saskatoon or any developed city, generally there's a municipal water supply that's handled by the city. It's handled by your government infrastructure. If, however, you're living on an acreage or away from a utility like that, you need to get water some other way. And the cheapest way is to usually drill a hole beneath your house until you hit some porous soil and or rock. And as long as that rock remains saturated, you can pump it out. You can pump the water out and use it. If you pump too much out, you're going to lower the water table and generate a bigger series of problems for yourself. So in this first scenario of rainwater or snow falling in this upland area, that's going to percolate and infiltrate into the ground until it reaches the water table where it's saturated. If that water table reaches the surface at a lower altitude or elevation, it's going to form a spring. If it's pressurized, it can form what's called an artesian well, and we'll see an example of that in a second. Water makes it past this spring. The water table is located here, this blue boundary, and we can see this house is removing water far enough below the water table that there's a chance for recharge, this local environment. They cheaped out in this house, didn't drill as far down, and the net result is eventually they've removed enough water that they've lowered their water table underneath their house. And the result of that could be that they eventually no longer have water. This house is going to run out of water as well, but it's going to take longer. These neighbors will be gone, therefore their water use will be removed from your neighborhood aquifer. These aquifers can be unconfined. This is an aquifer that has an aquiclude below, something that occludes the water or discriminates against the water. A confined aquifer, on the other hand, has an aquiclude above and below. So in this case, this can act like a pipe. This can be pressurized, and if it is pressurized, we get an artesian well. We can see that here, where we have a confined aquifer situated between two aquicludes. These are going to be beds of low permeability, low porosity, generally difficult for water to flow through. So difficult for water to flow through here, difficult for water to flow through here, easy to flow through here. So any of this snowfall and rainfall can be funneled into this confined aquifer. Now, the height of this aquifer is going to determine the hydrostatic head difference in elevation between the water at its highest point and the water where we're going to tap into it. So you can see here there's a significant difference in elevation between the top of the water table and the point at which we puncture it here, resulting in an artesian well, one that flows or sprays water out of the ground on its own. And again, that's because we have hydrostatic head here. It's a big tube, essentially, that's full of water. The height of that water in the tube determines the pressure at the base of the tube. So we can either have an artesian well that just flows, or an artesian well that blasts up out of the ground like a gusher oil well from the 1930s in Texas. Unusual environments include perched water tables. In this case, we have an aquiclude. We have an unsaturated series of rocks, bedrock, soil material up here. That's going to allow infiltration. The water is going to soak in and saturate this porous material above the aquiclude. And if this perched water table is located near an outlet, a geographic outlet, a geomorphological outlet in this case, we're going to get a spring. If the water is anoxic, you might see a reddish stain, a slippery, slimy iron hydroxide stain, and that implies that there's a significant amount of dissolved iron in the water, and it's dissolved because it is anoxic. So once it's oxygenated, it converts to iron hydroxide, and you have your slimy red hillside here. Or if you live on an acreage, you might have a slimy bathtub for the same reason. So pumping out this water beneath your house, you have to know the recharge versus discharge if you want to maintain a balanced system. So there's balance in the system if the water table is stable, if it doesn't rise or fall. If there's excess recharge, the water table will rise. If there's excess discharge, the water table will fall. And in a special scenario, a house or a farm, an acreage that pumps too much water out leads to what's called a cone of depression, unlike the cone of shame. This cone of depression is a downward deflection of the surface of the water table. So you'd have to drill further and further into the ground under this scenario to maintain your current water usage, or hope for more rain or fewer neighbors. If we remove too much water from the ground actually sinks. Water takes up space. That space actually elevates the land surface just like a sponge. The sponge we saw in the video long ago, 20 minutes ago. So removing that water causes the sponge, in this case the land, to sink and crack. We can see that here, an additional complication, where we've lowered the water table. In this case, we've lowered the water table to the point that salt water begins to rise up to replace the fresh water that's been removed. If we continue to remove this fresh water, eventually the salt water is going to get into our well and the party's over. You can't drink this water, you can't irrigate with this water, you can't do much of anything with this water except take a salt bath. We're in the Midwestern United States. We have a huge, very important aquifer named the Ogallala Aquifer. This supplies much of the agriculture and domestic water for a very large portion of the United States, the Great Plains. What we've been doing is removing much, much more water than is being replaced. And you can see how it's being removed here in this graph. So irrigation has increased from the 50s until around 2000 or so, and there's a slight decrease in irrigation use of water. Public water supply, likewise, flipping and flopping, seems to be reduced now. Thermoelectric power has maintained a somewhat steady use of water over the last 50 years or so. The result is we're removing a lot of water. These are billions of gallons per day. So 200 billion gallons per day is being removed from the Ogallala Aquifer today. How much is going back in? Well, not that much. So what's the deal now with this aquifer and the pipeline? Just to make things worse. This pipeline is proposed to run right through the most important aquifer on the Great Plains for the United States, where much of the food comes from. What's the problem? Well, a little bit of toxic oil from the tar sands in your drinking water makes the water what we call poisonous and cancerous and all kinds of other bad things. Once it's in there, how does it get out of there? Well, you wait 10 or 20 or 100, 200,000 years, and the bacteria will eat up the organic contaminants. The arsenic and mercury and that other stuff will stay there forever, so it's a gift that keeps on giving. So that's a problem. The fact that this pipe is going to go directly through the aquifer, not above it, but literally through it in some places, is even more troubling. Recent study based on pipelines, pipeline history, and rules and regulations suggested that there will be 91 major spills on this pipeline in the next 50 years that will spill somewhere around 7 million barrels of oil into the aquifer. If it takes a drop of oil to contaminate hundreds and hundreds of gallons of fresh water, it's going to be a big problem. Once this aquifer is contaminated, that's it. Done. So all the farms and people that live here that need water for some reason, like drinking or growing, are going to be cut off. In California, it's even more spectacular in some ways. We can see the subsidence of the land surface from decade to decade, century to century. So here, 1925, this would have been the surface of the land. We sucked a bunch of water out over the next 30 years, dropping the land surface to this level. Over the next 20 years, we dropped it down to this level. So we seem to be speeding up the process of dropping the level of the ground. You can see that here. Near Visalia, the land is dropping on the order of 50 centimeters per year, which is almost measurable. You can almost see the difference.